So now we're going to talk about explained and unexplained variation. And so specifically, we're going to explore the deviation from one point to the mean. And so we've got this situation that we're going to map out over to the right-hand side. And so first we're given that there is sufficient evidence to support the claim of linear correlation between x and y. So if there's sufficient evidence to support the claim of linear correlation, what this means is that the regression line is a good fit. And so we can use this regression line. Remember, if the regression line is not a good fit, then the best point value of any kind of y value is just the mean of y values. So we can use the regression line in this case. Okay. The equation of the regression line is y hat equals 3 plus 2x. 3 plus 2x. Well, let's plot this. So I know I've got a y-intercept at 3. And I know I've got a slope of 2x. And so starting at 3, I've got a slope of 2. What that means is that for every x value I'm moving to the right, I'm moving up 2 y values. So I've got a point here. And let's just move all the way over to 9. So from 0 to 9, I've gone to the right 9 places, meaning I'm going up 18 units. All right, something like that. And I'm going to try my best to draw the straight line because I know this is linear. Good enough. And so this is our linear regression line. Y hat is equal to 3 plus 2x. Our regression line. Now we're given that the mean of the y values is given by y equals 9. So this is the mean of the y values is y equals 9. And so what I'm going to do is I'm going to draw a horizontal line through y equals 9. This is the mean of all y values. Y equals 9. Now because this is a mean, I'm going to put this bar over the y. Then I'm given that one of the pairs of sample data is x equals 5 and y equals 19. So one of the pairs of sample data is x equals 5 and y equals 19. Let's just mark this point. Okay, then I'm given that the point 513 is one of the points on the regression line. And I can just get this from the equation. If I plug 5 into this x, I get y equals 3 plus 10, which is 13. So I've got this point on the regression line should be 513. Okay, I've successfully mapped out my situation. And so let's see what we're going to do with this. With this situation, we're going to just describe different types of explained and unexplained variation. And so if this was any real situation, we would always have a regression line. We would always have a mean of all of the y values, and we would have all of these individual points. So we're just talking about this individual point, 519. We're given that the total deviation is the vertical distance, y minus y bar, which is the distance between the point and the horizontal line passing through the sample mean. And so my total variation is the distance from this point to y bar. So I can find that by subtracting y bar from y, because this is just my point. So the total variation is y minus y bar. And what's that for this situation? For this situation, the total variation is just 19 minus 9. So that's going to be 10. Now let's look at our next type of variation. Then we have the explained variation, which is the vertical distance between the predicted y value, which we call y hat, and the horizontal line passing through the sample mean. So we've got the explained variation. This is going to be y hat minus y bar. And in this case, 13 minus 9 is 4. And then finally, we have the unexplained variation, the vertical distance between the point and the regression line. So we've got the unexplained variation. And we can find that by taking our y value and subtracting from it y hat, the y value on the regression line. In this case, we've got 19 minus 13, which is 6. And so now let's take a minute to talk about why this is called explained and unexplained variation. This is because, let's say I'm dealing with a situation like I have pictured, where I've got some sort of positive correlation between the x and y variables. Now I know that's this situation because here my regression line has a positive slope, meaning I've got a positive correlation. And so there's only going to be one point where the y value of the regression line is equal to the y value of the mean of y values, right? Where we're passing through the line that we've created by setting y equal to the mean of y values. So there's only going to be one point where these are equal. And so at any other point, we're going to naturally have some variation between the y value of any given point and the mean, because there should be a difference if there's either a positive or a negative correlation. So for the unexplained variation, there's no real reason other than the fact that this line is not a perfect line of fit. In other words, if our r is anything but positive or negative 1, why this point deviates from our regression line. And so that's why this is called unexplained variation, because an ideal regression line with a perfect correlation, a perfect linear correlation, would have all points lying along this line, but that's just not how it is, because most situations don't have any kind of perfect line of fit. There is no perfect correlation. And so this is why this is called the unexplained variation. We know the total variation, in this case of 10, is just the unexplained of 6 plus the explained variation of 4. And so this is the case for all given points. They apply to one particular point. Finally, we've got the sum of squares. If the sum of squares of the deviations can be found using all points, then that's the total amount of variation. And we talked about this in terms of the least squares principle. And as far as this total explained and unexplained variation, when we talk about all of the points, we're just taking the sum, meaning we're adding up all of these different measures of variation for each of these points. Now let's talk about this r squared term. Now we've talked about r squared. We talked about this in section 10.1. And we gave a definition, but we really didn't say much else about it. We said that r squared is the proportion of variation in y that is explained by the linear relationship between x and y. This value of r squared is called the coefficient of determination. So now instead of saying r squared, we can say this is the coefficient of determination. Now that we understand explained and unexplained variation, we can conclude that r squared is just because this is the proportion of variation that's explained by the relationship. We know back to statistics 1 that when we have a proportion, it's the number that fits the situation, so the amount of explained variation over the total. When we have a proportion of successes, it's always the number of successes over the total number of trials. So same idea holds here. And so we can either compute the value of r squared using this formula, but we're not going to do that. We're simply going to square the linear correlation coefficient r. Because we're finding this linear correlation coefficient using technology, we might as well just square that value. So example 7 says using the 23 pairs of chocolate Nobel data from 10.1, we find a linear correlation coefficient of R equals 0.801. So this is what we found in the last few videos. Find the coefficient of determination. Also find the percentage of total variation in Y that can be explained by the linear correlation between chocolate consumption and the Nobel laureate rate. And so this is what we're going to do. If our R value is equal to 0.801, then our R squared value, well, we're just going to square R. So that's 0.801 squared. I'm going to use a calculator for this. And we get 0.641601. Let's round this to 3 decimal places. We get about 0.642. And so finding the coefficient of determination, great, we found it. And now for the percentage of total variation that can be explained by the linear correlation between the chocolate consumption and Nobel laureate rate. Remembering that R squared, this coefficient of determination, is explained variation over total variation. If this is equal to 0.642, and so 64.2%, just converting this decimal into a percent, can be explained by the linear correlation between chocolate consumption and the Nobel laureate rate. Another point that's worth mentioning is what portion can't be explained. If we're asked what cannot be explained, well, this isn't in the question, can't we just subtract this from 1? I know total variation is just 1, right? And so I can say that 35.7% cannot be explained by that linear correlation. And can we see how this all connects? Because the higher of a percentage, the larger percentage that can be explained, the better of a line of fit this is. And that's why with our regression equation, if we have a high R, then we have a high R squared, and so a higher percentage of this can be explained. If we had a really high R squared that was closer to 100, then most of our data could not be explained by this regression equation. Therefore, this would not be a good measure of fit, and we would just use the mean.